Hi, hello. My name is Anna Wiśniewska, and I'm a postdoc at the Leibniz Institute for Astrophysics in Potsdam. And today I will be talking about frequency distribution of acoustic oscillations in the solar atmosphere during flare event. So first, I would like to introduce you a little bit what is helioseismology and observed solar oscillation. Then I will go through the seismology of the solar atmosphere and through solar flares. And I would like to show you frequency distribution of the pulsation in an active region during such an event. And then maybe I could show you what I want to do in the future. Okay, so helioseismology and the solar oscillation was discovered by Roger Lighton already in 1960s, and mainly it was based at the first time on the Doppler shifts of the spectral lines, and they discovered he discovered pulsation, and the velocities he found out was then 50 centimeters per second, and then later on Ehrlich and Dubner found out that this effect is actually the internal oscillation, and that waves are they proposed that waves are trapped inside the sun, so this is a kind of internal pulsation, which is now to be confirmed. And here you can see this Dopplergram, and this is based on the gong data, and you can see also that one side of the sun is going toward us, and the other limb is going backward. Okay, a little bit of theory. I hope that I will make it. So the oscillations, there is so many modes, several million of oscillational modes, and they are described by the spherical harmonics, which have some kernels, and the spherical harmonic function, and this is all in polar coordinates. And basically, oscillations are characterized by individual quantum numbers, which is n radial order, L, this is angular degree, and m azimuthal order. And of course, different frequencies or different modes penetrate to the different depths of the solar interior. And therefore, there is such a diagram which called power spectrum. And this is basically observed distribution of oscillatory power. And we can see here that the power is mostly concentrated in 3.3 millihertz, which means that the dominating oscillation in the sun is 5 minutes oscillation. So, and these are P modes. On this power spectrum, you can see that below the fundamental mode, we observe the gravitational waves. Here are the P modes, and here I put also some GIFs to show you if we have like a constant L, then if we change the azimuthal order, then we get several oscillations. Okay, but this was for the interior, so the same is valid for the atmosphere. And if you can see here on this scheme, solar atmosphere is inhomogeneous in its structure, and it depends on the region where we are measuring. And especially if this is like a local, when we are at some point of the solar atmosphere, we can see different features, which can be sunspot, quiet sun, or like some pores. And each of them looking differently at the different heights of the solar atmosphere. And you have seen now, for instance, photospheric level, and here is around the chromosphere. So to obtain like a kind of three-dimensional picture of the solar atmosphere, we need to go for the multi-wavelength measurements. And there we can also investigate waves using the same approach as for the internal oscillations, but we can use smaller field of view, and we can also construct or calculate same power maps for velocity and intensity signals, and calculate dominating frequencies. And here I would like to show you, these are the equations, basically the Fourier transform of the velocity signal and then power spectra, and basically you can see that the power spectrum is three-dimensional structure, so we average then it over M to obtain like a two-dimensional plot. And what is interesting here, what I would like to show you, I don't want to go too much into the details with that, but that for the various wavelengths, we observe actually different power distribution in this power spectrum. So this is measured in a 9 wavelengths, and you can see the last one is the H alpha, and we are going from the photospheric level, so I will play it again, to the chromospheric. Yeah. So in H alpha, you basically don't see oscillations. Okay, and now I would like to go a little bit to the flare. As you already heard before, flare arise as a result of magnetic reconnection, and then a large number of non-thermal electrons is transported downwards and then heated up the chromosphere. And response of the chromosphere can be observed in the H alpha line, for instance. And here I will show you such a very raw data measurement of the flare, but unfortunately I don't have better now. So we observed flare using ground-based measurement, and it was classified as a C2.3 flare. So we thought, okay, maybe let's try to see what is happening there in terms of the oscillations. Okay, and now we have two spectral regimes, and one is the level of the photosphere, and here you can see the H alpha plots. And the differences, you can see it probably already now. So there is a difference in spatial distribution in the level of photosphere, and this is probed with the iron line, and chromosphere looks slightly different. So in the chromospheric region, the power is mainly concentrated in the flare, so this counter indicates the flare position, and also in the postal route there is not so much. This is 2 hours before the event. And on the photospheric level, we can see the power enhancement basically in the two pores which were in this region. And in both cases, at the photospheric and chromospheric level, the solar atmosphere in the surrounding area has like this random mixed character. Okay, and then we will see hopefully the difference. So again, we are looking in a prior and shortly after the impulsive phase of the flare, and we see the change. I will show you now again the previous slide. Yeah. So we observe the change, and basically in the photosphere, the power decreases in the flare area and inside the pores. So you can see this is much less power here. Although in a chromospheric level, we observe the concentration of the power of the frequencies with a high power in the flare area inside the post-flare loop as well. And what is other thing which is very, very important here, that I divided these maps into different frequency bands. So you can see that basically waves which have, for instance, 3 to 4 millihertz oscillation, propagating a little bit different on this map than these for, like, let's say 12 to 30 millihertz. And this looks differently in a photosphere, which is like kind of finding because it was not observed before using this method. And we measured in the 9 spectral regimes. However, good for analysis was only 7. So I plotted for some chosen frequency band, let's say this is 8 to 9 millihertz, and we are going from 300 kilometers up to 2000 kilometers, and you can see the differences in the wave power when you're observing from the bottom to the top of the chromosphere. And this is finding which I think it would be great to investigate further, and therefore I go for the space data, and basically this is 1600 AIA data. And I'm sorry that I didn't upload this region, which is much smaller than this one, because this was 100 by 100 arcseconds, and here you have more. However, we still observe some power enhancement around this region which we're measuring. And therefore, I would like to go for the solar orbiter data to improve these results and to check whether this is really true. And yeah, I hope that I will find out something more using space data from solar orbiter. Thank you very much.
Thank you, Anita.